Bjarne Stroustrup has been a guiding force for this community and has done a lot of work to promote C++ and to build a community out of that. And so I'm looking forward to his talk today, where he's going to tell us a little bit about concepts and what that means. Thank you very much, Bjarne.
Thank you very much. Okay, wow. If I could see all of you, I would be intimidated. But fortunately, thanks to the lights, I can see about 2 lines here. So I'm going to tell you a little bit about concepts. And in some ways, that's a very old topic. In other sense, it's new. You can start using it. Some of us have been using it for years. It's getting into production places. So I'm going to talk a little bit about generic programming. Then I'm going to say what do we actually get out of concepts, and what are concepts, and how do you build useful ones. So basically you can go back to the early aims of David Moser and Alex Stefanov, basically wanting to get generic programming in as a discipline for writing more flexible, better code with a focus on algorithms as opposed to data types. And my aim is sort of fairly simply stated, making generic code as simple as non-generic code. This is one of these modest and ambitious aims that can drive development. So I'm going to do that. Obviously, when you have generic code, not all code can be as simple as if you're just writing code based on knowing that everything is a double, say. So more advanced generic code should be not unnecessarily complicated, but it can't quite be as simple as non-generic code. And one thing I would like to emphasize, and I feel I probably won't be able to do it as much as I would like to, is it's not just for foundation libraries. There's a lot of application code that is generic, and you shouldn't just think about it as something over in the standard library that you don't really need to think about. I was talking to a bunch of theoretical physicists a couple of weeks ago. It's there in their stuff. That's certainly not foundation library. I've talked to generic embedded systems programmers that use it for certain aspects of device controls. This stuff, concepts, is not just esoteric, it's not academic at all, and it is not just for foundation libraries. Basically, the whole game is to write better code. And better code has all the usual requirements here. Nothing here has much to do with generic programming, but the point is that if you write generic programming, good generic code, it helps with all of those things. And it's basically a significant help. I really don't like talking much about individual language features. A language feature in isolation is usually boring. And you can talk about where you put your commas and semicolons, and some people like that. I don't. I tend to fall asleep over that. It's necessary at some level, but I'm trying to get the big picture. So this is not a talk about language technical details. If you want to know the latest about the debates in the standards committee, well, go to one of the other talks, or to the committee panel or something like that. This is not what I'm trying to talk about. And there are at least 4 talks at this conference that goes into details about generic programming and concepts. So that's another good reason for me not to go into those details. So the concepts have been moving through the standards process, too slowly in my opinion, of course, but I'm known to be impatient. And basically the TS was approved 2 years ago, and we have the explicit requires clauses in the working paper now. Barring utter disaster, it will be in C++20. We have the shorthand notation so that you can, instead of just saying I want a type "and," I can say I want a random access iterator, and we have requires expressions to express things directly in the language. Not quite yet. We hope to get ranges into the working paper in San Diego. That's less than 2 months away, and again, that seems that it'll work, which means that your algorithms and containers and stuff like that can start using concepts, and you get the benefits right out of the box with C++20. There's work going on the function declaration-like syntax. That's not settled yet, and my guess is you won't get the concept type name introducers. If you don't know what that is, well, tough. You can find out, and anyway, you probably won't be able to use it in production for another couple of years. It's all available in the GCC implementation now. So my main sort of thesis here is that generic programming is just programming. And my aim is to make this more true than it is now. And this implies that we need to improve some of our type checking to make type checking for generic code much more like checking for ordinary code. Eventually the generic code will be ordinary code. We need to improve the syntax. The template syntax is clunky. It has been clunky since the simpler syntax didn't fly in the 80s. And we have to organize our code for generic and non-generic code in the same way. Not all of this header stuff for templates and .c for CPP for code. That's the modules stuff, so I'm not going to talk about that. So basically there's a history to this. In the 80s, most of the 90s, if you wanted to do generic code in C++, you ended up using macros. And I have a paper from 81 that says we need generic programming and macros will just do it for us. I was right about the first part and I was very wrong about the second part. Macros just poisons everything, including your IDE and your editor, and scrambles your brain. So we have to do better than that. In 87 and until now, I have some fairly specific aims for templates. I want them to be flexible. At the time I said I don't want a language that can only do what I can imagine. I mean, maybe my imagination is good, but it sure isn't as good as the union of people in a room like this. And I want a zero overhead. Otherwise, people write this sort of ugly pointers and array kind of code that they then think is more efficient. It often isn't, and it's certainly less maintainable than good generic code. So it had to have zero overhead. This is C++. It has to be used for really critical embedded system stuff. It has to be used for high performance stuff, and it is today. And then, of course, I wanted good interfaces, because good interfaces is essential for large software. That's how we partition our code. We only have two ways of simplifying code. It's abstraction and divide and conquer. Divide and conquer means putting a barrier between two parts of the code, and we get there. And as I used to say, 2 out of 3 ain't bad, but it isn't good either. So I've been trying to figure out how to get away from the basic templates, unconstrained templates, header-only organization, because it's fundamentally not right. It may be good enough. We've done superb things as a community in this period, but we can do better. Okay, so let's take the time machine, go back to 78. And that's how we wrote code. This is KNR code. We say that square root returns a double, we give it a 2, and it crashes, of course, because 2 happens not to be a double. Well, so what? Well, we didn't say it was a double. All we can say is we can go over to the source code and look at it, and it says that square root takes an x and it treats it as a double. It does not say you must give it a double or you get an error, get a runtime error. No, you get a crash. And I had sort of one look and another look at this, couldn't quite believe what I was seeing, and made some changes. In the first 2 months of the C++ project, civil classes that was called. So now we can write double square root of double. I mean, I want my square root to, I want the declaration to say that it expects a double, so that if we get square root of 2, I get the right answer. It converts 2 to 2.0. Similarly, if I give it some rubbish, like a string, I get an error right there. This made a huge difference. And I also cleaned up the syntax so that the definition now looks like the declaration. And if you've been writing C++, you've probably never seen anything else. If you've been writing C in the last sort of 30 years, you've been seeing things roughly like that. And it's an operation like that that I think we're trying to do with concepts relative to checking. Go back to 88, and we're saying that there must be a type which we will use as an iterator. And since we don't know too much about the interface, it just says there must be a type, and we'll use 2 of them. It has to be in the header file so that we can do some compilation. And I can say a vector of integers, that's fine, list of integers, fine, vector of s, fine, everything works fine, so we start using it. And then sorting vectors happens to work. Sorting lists doesn't work. From deep down in the implementation of sort, we'll be told that there is an absence of a subscript or a plus or something to some type that we probably haven't heard of, because it is it's an implementation detail. And if you want to sort the vector of s, well, because we couldn't get default definitions of equality and less than for types, it'll just tell you that you can't compare 2 structs. And the error messages are spectacularly bad. This is because we have duck typing. If it looks like a duck, if it waddles, and if it quacks, it's a duck. Unfortunately, of course, it could be a rubber ducky or something like that, and we get these strange errors. We really want to be able to say that we want something better than just a type. And on the other hand, templates was a massive success. It's one of the things that kept C++ going, and at the edge of things we have flexibility, type safety, specialization for irregular types, and the basis of much template metaprogramming, and a lot of type-based optimizations. The result is great flexibility, great performance. And it has huge flaws, as I pointed out. The syntax, I mean, even its mother couldn't appreciate it. Duck typing, error messages, the overloading with templates is really quite complicated. Code organization gets messy, and the compilers get slow, very slow. We have to do something about it, and I would like to address all of these aspects, not just fiddle with the corners of it. So let's see what I want and what we're getting. I would like to say that sort takes a sortable. Concept is the specification of what is sortable. And you can look it up in the standard. It says that you have to have a begin and an end. being a sequence. It has to have random access, and the value type, the element type, has to be something you can compare. Fine. Unfortunately, in the previous 20 years, compilers and users don't read the manual. However, now we can write this so that it works. I am using the concept TS notation just now, because then I can test my code. This is not likely to become C++20, but it's in the TS. So if I sort a vector, it matches the requirements of a vector of integers. It matches the requirements of sortable. List doesn't, because it doesn't have a subscript, doesn't have random access. And sort of the S's doesn't, because the value type doesn't have the comparison operator. So I get an error right there. And it should be readable. They will become even more readable over the years when things get tuned to use concepts well. And now I can now sort anything that's sortable, and the implementation of sortable could simply be to call the old sortable. And if we want to be more flexible, I can say I actually would like to sort lists even though they're not sortable. They don't have random access, and so we just define the notion of something that list-like, which has the properties of being a sequence with elements that you can compare, and I can implement them by putting them into a vector, sorting them, and putting them back again. That's simple and quite often a reasonably performing regulation, and if we do this, once it sees the list, it will say, oh, I can't do the simplest sortable, but because I lack a property, but I have enough properties to call the list, so we'll do it. So we're getting the overloading, just like we got the overloading for ordinary types in the standard language, well, almost 40 years ago. And the rules for overloading, you can look them up, are much simpler than for basic types. And by the way, as ranges are now coming, we can simplify. See, why do I have to say begin and end all the time? I mean, one of the principles that we're trying to work towards is to make simple things simple, and the simplest case of sorting a sequence is to sort all the elements of a container. Anything, you just give it the whole range and it'll figure out what the details are. So things are improving. Notice also I didn't say what the element type of the vector is. I can now deduce it. We are moving ahead, and it's getting simpler to write good code. So if we look at it, when I want to make ordinary code and generic code the same, I have to think about types. And I have to think about how concepts fits into the type system. And a type basically specifies what operations I can use on an object, implicitly or explicitly. And it relies on function declarations and language rules to make sure this works. And in addition, a type specifies how an object is laid out in memory. So it says what can you do to an object and how can you make the object. A concept, on the other hand, basically specifies how you can use an object, how implicitly or explicitly what operations you can use, and that is specified in terms of something called use patterns, basically expressions, and it reflects the rules of the language. And it says absolutely nothing about the layout of the object. And ideally, that would be the only difference between types and concepts. We are close to that. So you can think about simple objects, concepts that only take one argument as basically something that is how to use an object as opposed to how to make it. Okay, so here's an example, types and concepts. I have here a concept which is same, which says that a capitalized int is really an int. And I can now start writing code with that concept. So x1, it will take anything that is an int, and 7 is an int, so it'll do it. Or I could use the integer directly. I can do operations, and again, I can say for the capitalized int, I'm saying the result must be something that is an int, and the other one, it says it is an int. And I can pass arguments, and I can overload on it. This looks very, very similar, and it is deliberate. I even thought of using a font that will make it easier to tell the difference between the capitalized int and the lowercase int, and decided no, actually the point is they're similar. The syntax here met immovable objections in the standards committee, so it's unlikely you'll be able to say sort of sortable. You will probably being able to say sort of sortable auto stuff. People seem to like that better. It's a compromise proposed by Ville Voutilainen, so you can get very close to what I'm saying here. One of the main reasons there is a discussion is sortable of ref. If that is if that was a concept, then it would be a template, and the ref would be a forwarding reference. If not, it'll be an R-value reference. I have taught concepts for about 5 years to many dozens of people, talked to many hundreds of people. I've never seen this kind of stuff in real life, but that's a fact to the standards committee, and I think I can live with what we are likely to get. So that's sort of as much as I'm going to say about what the technicalities about concepts. I'm going to talk about what benefits we might get out of it. By the way, my section breaks has people who contributed to this. Andrew Sutton there is the initial implementer of the stuff you can get in GCC now, and he's worked very hard on specification and implementation. So basically, concept supports good design. And they are doing to design using templates roughly what classes did to ordinary programming. It allows us to structure our code better. It allows us to think about code better. If I'm going to call something with a couple of points, like draw a line, you can do it the old way, int, comma, int, comma, int, comma, int, and start wondering what the ints mean. Or you could have point, comma, point, or point, comma, box, and be more specific about what your sign is. That kind of way of changing the way you think is what we are after it. It gives better reliability and better maintainability. I have some practical experience with that. And again, for overloading, that's important because overloading is the basis of generic programming. If things aren't called the same when they're doing the same thing semantically to different types, you can't write generic code. We have to go there. And so let's see some example here. Here's the classical example, the slightly simplified version of advanced from the standard library. We can say that if we're given a forward iterator, we have to do things a slow way. Dum, da, dum, da, dum, da, dum, da, dum, go forward. If I get a random access iterator, I can just go over there in one hop. This is a very important difference, and we have it in the standard library. Now we can write it as simply as this. Basically, give it a vector, and advance is a very simple operation, O1. If we give it a list, it will be a relatively slow operation, ON. And basically getting this kind of stuff simplifies our code relative to what we have to write today and makes it much more similar to other kinds of code. And note that we are not actually saying you have to write a concept hierarchy and make your code rigid and only do the things that has been pre-declared to work. Concepts are predicates. We just figure out which predicate matches the best and get on with it. The code is simpler. So yeah, as I pointed out, overloading is fundamental to generic programming the way we do it in C++. We've been using a lot of traits, which can be quite complicated. If you looked at code using enable if, you know it can be headache inducing. And also the workarounds using these programming techniques on basically untyped code, the fully generic stuff, it gets quite complicated and slow to compile. Type checking happens at the end, at the very last moment, and that's at least it's type safe for some definition of type safety, but it doesn't give the errors up front, and it gives the compiler a hard time. So let's see an example. Conditional properties, they're very widespread these days. Basically, we want to say that something like a class offers a property if and only if another type behaves in a certain way. So here is the classic pointer type. A smart pointer, it could be a unique pointer, it could be a shared pointer or something. All of them does the equivalent to what you see there. You have an operator dereference if and only if the element type is a class. Otherwise you have to dereference. So that's expressed very directly. You get a dereference. It requires that T is a class. Take a more complicated example. I have a class pair, still borrowing examples from the standard library and still capitalizing my types so that you know it isn't really the standard library. So I want to be able to make a pair out of two values. And I want to make the pair out of the two values if and only if each of the two values can be converted into the appropriate type of the pair. And so I write this. There are two element types. If their types are convertible to the appropriate da-da-da-da-da. In other words, the code reflects very directly the way I expressed what I wanted. This is nice. To compare, for those of you who haven't seen too much enable if code, here's the simplest version of the pointer version written the old way. It says that there's an arrow operator, a dereference operator, if, well, you can see the stuff there. This is sort of painful, and in particular, it's not universal. You can't use the same technique everywhere. I was thinking of showing the pair constructor, and I decided not to because I had trouble fitting it on a slide. For starters, there's no place in a constructor to use an enable if. Secondly, you have to deal with a variety of situations. It gets very messy. Concepts maps the way we think about our problems. The workarounds do not. So we simply cut out a part of the thought process. That's good. Some people who has tried to use auto and fully generic stuff has found that it leads to some problems. Every new feature gets misused and overused. That's fine. I love auto, and so does a lot of other people, so it gets overused. And one thing we found was that people call a function and they put the result into auto. That's reasonable if there's generic code, you don't know the exact type, or you don't want to bind it to a particular type just yet. So you just bring the generic code forward, and you get things like foo bar x of y, you put it into some value of some type. Fine, except we find that the programmers keep looking into the header files and flipping forwards and backwards in the code, and readability is seriously decreased. This becomes a bug source. So the response for now has been put a comment in. Every time you assign something that's not obviously of a type, put a comment on it. Sure, make shared, you don't have to have a comment because you know make shared makes a shared pointer, but a lot of cases, if it goes beyond that, you have to put comments in, and your code gets uglier, larger, and comments are not always right. With concept, you can say, well, I'll take anything as long as it's an input channel. And you can do that in any context. That clears up code a lot, eliminates programmers flicking back and forth between different parts of the code, which is very distracting and breaking concentration, and you just get much better code. Readability is one of the benefits of concepts. And then, I don't know, familiarity is a strong force, but you look at that template there, it's really quite clunky. And for new things, they're scary. People want prefix keywords, and that's how we got to here. Names become very important because there's not really a type system here in play that says what the type name really means. I mean, type name input iterator means I hope that the input iterator is an input iterator. It's just a matter of hope. And this was what we got out of some historical process where people were a bit panicked over templates. They were very new at the time. When we can be specific, things get far more readable. The version up there is slightly longer, but it says much more. It says, I'm going to get an input iterator, and I'll take any other type as long as it's in equality comparable with the value type. Let's see, I don't have a definition of value type there, but that's the one that looks in and finds what the value type is, the element type. And with auto and type name, we have to read the implementation again. We're back to the sort of the KNR style of C declarations. There's simply not information enough. And here there's people who look at the top and says, ooh, that's complicated. It isn't really. It's just unfamiliar for a day or two. I know from students that on day 2, they wouldn't go back. And so, oops, I'm going the wrong way here. Sequences are expressed as pairs of iterators. We are going to move forward. We're going to get the range TS, so we can stay, instead of saying there's a pair of iterators, we can say I want a range, however expressed. And you get to the lower version there. It's important that we are now moving from the sort of language experimentation to the supported use of things with standard library support and such. And by the way, don't expect optimal readability from older code that has been bug compatibly moved forward to use concepts. And don't expect the most readability to come from the deep foundation libraries that has to have the ultimate flexibility. I've observed that the most benefits from readability actually comes from relatively simple and relatively new libraries written by people who understand concepts, as opposed to people who understood the old techniques very well and replicates them using concepts. So we still have a ways to go to overcome the ways of old think that leaves the complexity in place expressed with the new facilities. So again, back to this notion that auto and type name is the weakest form of typing. It simply says it's a type. In theory, we could actually do without having auto in the language. Look at that concept there, capital auto. That's the way we could do it. If we started designing C++ today, quite likely the built-in feature auto could be eliminated. And my aim is that you would accept you can accept a concept wherever auto is now. That's backwards. I really would like to use the fully generic concept auto if and only if there isn't a more precise way of stating what I'm trying to state. And that's a good. And again, this has been around for a while. I proposed auto, F of auto, in the Standards Committee in 2003, and the screams of horror were rather loud. Basically, in C++, we tend to rely on types and find things like void star and sort of suspect. It's a code smell. And I think we will get to the point where we think the type name and auto will be, well, a code smell. If they're there, somebody hasn't thought it through. At least if you have an auto or a type name T, there will be a required clause coming later to see what it means. But we really need to get away from this fairly primitive thinking that we take a type and we do something with it, and we try and write code that doesn't work if you get something that is slightly wrong. Anyway, it gets complicated. So concept will change the way we think about it. It's not just a hope. It's what I have observed again and again with people who have learned this kind of stuff. And this is not just support for business as usual. This is major. It changes the way we think. As I think I said, I'm not keen on individual language feature talks and details talk. This is not a detail. This changes the foundation. And the community as a whole is going to be slow as usual. It takes a long, long time to get millions of people to change their mind about anything. And there are people who will never change their mind. But individuals can do much better. So even if we can't get everything we want in all the code now, maybe you can do better in your local code. And maybe you can start experimenting even if you can't deploy it yet. That's what I and others started doing a few years ago. It works. First experiment, figure out what works in your context, move on, and it can get to the production level. GCC has pretty good support for concepts. Clang is coming. I believe Microsoft is thinking hard about it, and it's not really that hard to implement once you get going. And the standard library has it, so come C++20, we should all be there. So it's time to get ready. Concepts weren't born yesterday. There's a lot of people who say, oh, it's new, it's dangerous. Or as opposed to, oh, it's new, it's great. Or it's new, it really should have been something else. No, it shouldn't have been something else. We have spent a lot of time figuring out what fits with C++. And how to work it in, how to work the details. Alex started in '81, called algebraic structures, and then he's been calling them concepts since somewhere in the 90s, early 90s, I think. No, late 80s. And I tried to find a way of constraining templates in '88. It failed. Neither I nor anybody else knew how to get all three properties I wanted, but we have it now. The STL was specified in terms of concepts, even though there was no language support for it. It's a fundamental way of thinking, and therefore it makes sense to talk about concepts even if there's no language support for it. And then there's a lot of history here. I'm not going to go into it. That's a different talk, but don't think it's something new or something totally malleable. Good people have worked hard on this stuff, especially him. Okay, I haven't actually said that much about what is a concept, and now I should. And Alex says concepts are all about semantics. This might surprise you because there's no semantic part to the language support. However, it says what kind of properties a type must have, how can you use it, and you have to think about what that means, what makes sense. So basically, technically, concepts are compile-time predicates. Forward iterator T, it's true if T is a forward iterator, and it is false otherwise. And that can be used in the language and the language rules. That's the idea. What a forward iterator is, we can define somewhere else. We know what it is. We can look it up in the standard. And concepts are fundamental. They tend to represent fundamental concepts of our domains. So if you're mathematically inclined, you have concepts like monoid, group, field, and ring. In C++, we have input iterator, forward iterator, bidirectional iterator, random access operators. These are there today. We just have to represent them with language support. And so we've always had concepts. I mean, you read KNRC, the first definition says an integral type is, an integer type is. These are concepts. Now, today, we can actually represent that in C++. But we've been using that for some definition of we for more than 40 years. And we have direct language support. So this is philosophy. You have Plato. This is the engineering. Archimedes. He's an engineer. And we must learn to use the techniques well, not just philosophy, but actually practical use and practical support. And the concept is good if it represents a well thought out concept. It is not the minimal requirement for an implementation. We've been spending some time doing lifting and trying to find the absolute minimal requirements of an algorithm. That's not it. The ability to add things is not a fundamental thing for a large group of things. The ability to use ++ is not. You need something more well thought out, and there's no semantics to an individual operation, but there is a semantics to a combination of operations like plus, minus, multiply, and divide. And good concept should support interoperability. So, okay. A lot of people think about concepts as types of types. And that's not it. You don't do too much harm thinking about a concept that takes a single argument as a type of a type. However, most concepts take more than one argument. If you have a template that takes 2 type arguments, almost by definition there will be some relationship between those 2 type arguments. Why else are they type arguments to the same function, to the same algorithm? There has to be a relation. You're using them in combination. The second you'd have 2 arguments of different types, you need a concept with 2 arguments, and you're out of the type of type world. The other thing is that, like templates, concept can take value arguments. It's not that common just now, but since we now have value arguments of different types in C++ 17, 20, it'll become more common. So some of the concepts takes things like a type and a value. This is not type of type kind of stuff. And if you look at it, that means that concepts are not type classes, and they were not meant to be type classes. It's supposed to give you implicit conversions, mixed type operations, which people have insisted on since Fortran, and that type theorists have disliked since about the same time. But this is C++. We have to serve the C++ styles of users and the C++ users. And they are not expressed in terms of sets of functions either. We tried that, it didn't scale. So one thing to remember when you define concepts, when you think about concepts, is describe the concepts for clusters of operations. I mean, plus, minus, multiply, divide, and then you also probably need plus equals, minus equals, plus plus, and such. For stacks you have push and pop, and very rarely does a concept characterize a single operation. Has plus and has minus are very suspect when you see them as concepts, because they don't actually work in lots of places, and they are used for ad hoc combinations of features, and you get a set of operations that doesn't actually interoperate. So you have to think about that. Here's a plug-and-play example. I wrote a simple implementation of a sum. Could have been accumulate or something, but I wrote it in terms of plus equals. If I did the minimal dependency on that, I would have a dependency on a plus equalable, something like that. Beware of the dreaded ables. If your types have an able at the end, think a little bit harder. There are useful concepts that is named like that, but most of them aren't. So basically, when I want a system, a constraint for that algorithm there, I have to think, how else might I have expressed that algorithm? Should I just take plus equal, or should I take plus equals and plus and equals? Basically, some kind of number is a better answer, because you actually also want to have copyable, unmovable things you didn't think about just when you were doing it. So if you want to express the concept, you have to raise the level of discourse to something that makes sense, basically in isolation. What is it that I'm really relying on? What is the fundamental concept we're doing with? Here, it's at least an additive monoid, but I would say a number. It's not just for algorithms. Here's a piece of code which happens to be a very minor simplification of some real code. It is an input channel. It takes some transport and a message decoder. What's an input transport? Well, that's a concept that says what it is. And what's a message decoder? There's a concept that says what it is, basically saying what you can do to them. And then you build up some context, and then you have a variadic template here that is used to initialize the representation of the transport. This kind of stuff is really quite hard to write and understand, and it's really hard to explain to new developers unless you have the conceptual framework provided by the concepts that also gives you the error handling if people misunderstand this kind of stuff. So you can build it, use it for large frameworks. Let's see, how do we define concepts? There's Gabby Dos Reis, who worked with me and others for many years for building up this kind of stuff. If you are going to use some concepts, obviously the first choice is to find some concepts that somebody else has built. I have a slide of some sources, but basically the range library and the working paper from the standard has examples. But if you have to build your own one, the best thing to say is that you can build it out of existing things. So I talked about sortable. A type T is sortable if it is a sequence, meaning it has begin and end, has random access, means you can subscript and add, and its value type is comparable. It has the operations there. This is not brain surgery. This is not rocket science. though I'm sure we're going to use this in stuff for brain surgery and rockets. But this really is just a notation for the way we talk about these things. We have hit some fundamental top concepts, and it becomes easy to talk about them, easy to write them down. If you go down and want to define some of the simpler concepts directly, instead of using things done by others, like in every other area, you get to more complication and more trickery. It's easy to say square root of 2, but if you're going to write a square root, you have to know a little bit more. Are you going to use Newton-Raphson, and how do you express it, and is there a better algorithm? The minute you go down one level of abstraction, things get more complicated, sometimes very much more complicated, but in here it's fairly simple. I want a type to be equality comparable, comparable equals. So there is a support in the language called requires, which says that it can specify what the properties of expressions are. So it says that if I have two t's, they have to be able to be compared with equals and non-equals, and in both cases they have to return a bool. It's, again, not brain surgery, but it's more complicated than that. And you can get to slightly more complicated things. The way you get closer to the core language, you have to represent the facilities of the core language a bit better. So a sequence requires there has to be a value type, there has to be an iterator type, and those are things I've just defined up there. And there must be a begin that gives an iterator. There it is. There has to be an end that gives an iterator. And the input iterator, the iterator of t has to be an input iterator. I mean, it's not just returning a type called an iterator. We can actually say that it is an iterator, or else we're in trouble. And by the way, the value type of the iterator must be the value type of the type t for comparable. So that's one way of doing it. Now we're getting down to the level. We don't usually get much deeper than this, but if you look at the definition of the range library, you can see that as we go down closer to the hardware, to the trickier bits in the language, they get more complicated. If we can stay there at the top slide, it's better. And if we can stay out of this, it's even better. Like our fundamental functions like square root or sort, we get them out of the library. So do we get our concepts. There are in the working paper a concept session which has concepts, so that you will never actually have to do equality comparable and such, because they're already in the standard. Ranges, just about anything to do with algorithms and iterators, and there's more places to find them. One thing to remember is I emphasize the importance of complete concepts with semantics that make sense, they're fundamental. How do we get there? Well, there are two things. During development, we're almost going to get it wrong the first time. So we need to get there somehow. Secondly, sometimes we need building blocks. So take an example here. Here is sort of an ad hoc thing. It says that requires something that you can add. That's usually a mistake. I consider requires a code smell. If you see that in your code, you probably haven't thought hard enough. Because usually when we want plus, we also want these other properties, like you can get a plus b, but you can also increment and you can copy the thing, and quite often you want to construct it from a zero, things like that. So if you write some in terms of a concept, you can improve it as you go along. This kind of requires, which I've seen in far too much code done by people who are just coming to concepts. They think, well, I know the syntax, I can write these things, just show me the syntax and I'll write. You get this kind of stuff. And then these requirements starts growing. And they don't lead to interoperability because each operation is done by itself. What you need to do is to think about what can you do, what can you build up. Now, addable is one of these dangerous addables. So you think, is it really what I want? Don't I want a number? Don't I want minus also? If I don't want minus, why don't I? The minute you generalize sum to accumulate, you are up into the next level of abstraction where you need a proper concept to constrain what you can do. There's been people complaining about you can get accidental matches. If we are calculating what a use of a concept matches various concepts, you can get things that could accidentally match. And I picked here an example from the old days of object-oriented programming where people were worried, sometimes reasonably. Drawable. I define something drawable. It's something that you can draw. Be suspicious. It's only got one operation. It's unlikely to be a good concept. It may be something we did just at the beginning of a development before we knew exactly what it was. But be careful. It's got a single operation. It's called able. Be careful. Anyway, so we make a shape. It draws. We make a cowboy because in the games industry it draws. And so now we can do a draw all and it draws all. Now this is all right if draw really is the shape that draws. It's not so all right if it pulls a gun. So that's an example from the early days of object-oriented programming, just translated into to modern terminology. Accidental matches can happen, but really that's a bad concept. It doesn't represent anything fundamental. If you have done this properly, there would have been more draw operations than just draw, and it's unlikely the cowboy would have had them all. Similarly, for a cowboy, there would be operations that probably didn't fit with a shape, like get on the horse. So the accidental match can happen. It definitely can. Classical examples, input operator and forward iterator, they only change in their semantics, not in the set of operations. And if they do, you can add a disambiguation operator. I mean, there's things that forward iterators can do that input iterators can't. Add a go back to the beginning operation or something like that. It's not that hard. Or you can use a trait class. They still have their uses. But beware of the single constraint concepts. Here's a thing that I found. I started, like a lot of people, with a concept like a number that had the 4 operations, and then I realized that I needed that one. Then I realized I needed that one. But notice one thing. My initial concept, the incomplete concept, was useful. It caught a lot of the errors and allowed me to think, and I could just improve it as we went along. What's missing here? The fact that numbers can be copied and moved. So I haven't quite gotten there yet, but you develop these once at a time. Refinement of concepts in our minds is a gradual process as we learn and we improve our concepts. They have names, so we can do it. One thing that concepts do not do, concepts as designed for C++, it does not catch all type errors and template definitions. This was a bit of a surprise to some of us. If you read the early papers, it was one of the things we wanted, and we didn't get it for a variety of reasons. Here, Do we really want to catch this early? So forward iterator, and it does an add. Yeah, it would be good if we could do it, but as a matter of fact, doing that puts constraints on the performance, puts constraints on the compilation feature, and it actually constrains things rather dramatically. And this kind of error will eventually be caught, but only at instantiation time. We're falling back to the bad old techniques for catching the errors. On the other hand, it allows us to write simple concepts simply and to have fast compilers and be very, very flexible. And I have a set of rules that I'm following from the DNE, expressed in the DNE book. It's more important to allow a useful feature than to prevent every misuse. So why not? Basically, we decided when we started redesigning concepts after the C++ OX debacle that 90% of the benefit came from use checking. And we figured out how to do use checking with the current notion of syntax. Gabby did some experiments. We know how to do it. It's just we got more and more worried that we were wrong to close the system like that. How do I build these concepts up slowly before I know all the constraints? How about debug aids? How about telemetry, logging? If the concept has to be complete so that you can check and catch everything that you use in the implementation that you didn't mention in the interface, then you have a closed system and you sort of have to reach a level of perfection before you can use it. And since you don't, because perfection doesn't come early, you keep changing the interface. You want a debugger, you have to add debuggability in the interface. You want statistics added to an old concept, you have to add that to the interface. Now all the user code might break. So we were beginning to get very worried about how you do a transition from existing code to new code. How do you use old code from new code? How do you use new code from old code? We decided we are not going to touch definition checking for now. This actually requires serious thinking, not just the fact that we know how to do it is not sufficient. Just because you can do something doesn't mean you have to. Okay. You can still do some checking, like static asserts. I want to know if my type matches the range concept. There it is. And for testing of my algorithms, I can just build what's called archetypes, sort of a class called sort of X that has all the properties that I'm expecting. And you feed that into a static assert with my algorithm, and you see if it works. The only snag is that you are likely to make the same mistakes when you are defining the archetype as you did when you defined the concepts. This can be, of course, mitigated by having different people involved and such. But just because there's no default definition checking doesn't mean that there's no checking you can do, because, well, you can. You can just see it there. This works. Let's see. We would like to use high-level concepts more often. And so here's sort of a first cut on constraining merge. Merge is a standard algorithm, and it's one of the more complicated ones. And so the first cut looks like this. I need 3 types. The first one is a forward iterator, the second one is a forward iterator, and the third one is an output operator. And you have to be able to compare and assign to all of these things. This is somewhat tedious, and that's what the standard says. But we are doing the equivalent of sort of doing primitive operations. in the real world we've learned we have to aggregate operations into functions and classes and such. And so this is sort of, it's easy to make a mistake when you write so much and it's hard to read. One of my favorite phrases, header-egg inducing, and accumulate is much worse. And by the way, this particular pattern appears, I think, 4 times in the standard. So what we do is we design mergeable, which is the concept that requires 3 types and then does all the checking. So we need to get away from the most simple-minded things, often starting out with single type concepts and then going into the relationship between those concepts, and simply saying, I want 3 types and they have the proper relationships among themselves for being mergeable. There's a more elegant way for doing that, saying I want to introduce 3 type names and they should be mergeable, but that's not going to make it into C++20, though that is my favorite for expressing this idea. And basically then you just have to define mergeable, and mergeable is the one that has the properties we required. And obviously this has the point that this has the advantage that if you write your code like this, you can improve that concept as you go along, because the first time you're not going to get it right. So having it named is helpful. Having it in one place to fix it is helpful. It is just like when you're defining functions. You are defining functions. So the principles of concept design is basically think harder about the semantics, think harder about the fundamental concepts. This is why concepts are called concepts, by the way. And you have to think about what is universal, what can be used in many places as opposed to ad hoc. If you find you write a lot of similar concepts and a lot of long, complicated concepts, like if you see something like that, it's like seeing a whole lot of statements in a large function. You should eventually get used to thinking, oh, that's a code smell. It really, are there something that you can abstract from it and build something manageable like that? And you can actually predict that you're going to find in this case, so it's better to introduce the name concept earlier, even if you can't do all the details yet. Consistent set of properties, you make them concrete by using concepts. And basically, it's much easier to think about your code in terms of concepts. Again and again, I have met people who says, well, I couldn't even think of this solution without concepts. Just like I've met people, I can't even think about this solution without classes. It's a fundamental thing, it helps thinking. The major inspiration for a lot of this is Elements of Programming by Stefanov and McJones. I stopped Don Backers was in this picture, so it's interesting. He was the one that did Fortran, by the way. So there's a certain continuity in the programming world. And so concrete suggestions, make sure that you can think about the semantics. When you see a concept, it's expressed in terms of syntax, but you should be able to think about it as having semantics. Eventually we may get support for doing that. That will be called axioms, but we are not there yet. Incomplete concepts are far better than no concepts. And basically you tend to start thinking, then you have simple concepts and let them grow later. Use name concept requires is a code smell. You can use static asserts to get upfront testing of your types and your concepts. Define the algorithms in terms of general types. The ideal is plug and play, not absolute minimization. And variables should be constrained with concepts so that you don't have to write in a fully functional style and you don't have to fix the type too early to be able to get readability. This improves readability. And basically, for those of you who haven't already been using concepts for months or years, try them. I have not personally met anybody who tried them and went back to untyped templates because they wanted to. It's quite often that you have to go back because the implementations are not universal yet, and code bases cannot always be updated to the latest compiler and all of this stuff. But I think it's much better if you try concepts and suffer withdrawal symptoms for years after till they upgrade the compilers and the code bases, then you don't think in terms of concept, because you will not go back. Once you have used concepts, you think in terms of them, and it improves your code even if you don't have the language support. This is the underlying argument for that, why this is fundamental and part of the basic structure of the language. And basically, good interfaces is key to good code. You can do it now. You simplify the code. There's a lot of complicated template metaprogramming using enable ifs that gets radically simplified by using concepts. So if you're saying, no, I'm not doing generic programming, I'm doing template metaprogramming, there's two things wrong with this. One is the word template. Metaprogramming doesn't have to be templates anymore. A lot of const expert functions will help you. Secondly, concepts help with template metaprogramming, because not all of template metaprogramming is untyped. And basically, the thing that people always say, well, you want concepts because it gives better error messages. No. You want concepts because of all of these other things, and as a side effect, you get better error messages because you have expressed your ideas more clearly so that even a compiler can understand you. Okay, and of course, fewer errors. That's what I have to say, so questions? Do we have microphones? No microphones? You can probably yell loud enough for me to hear it.
I understand that the major use of concepts is to specify outputs, and this is a very useful way of building and defining software. But your example with mergeable seems to contradict this idea, because mergeable is that double concept that defines single operation rather than defining output.
Yeah, so the question is that he'd gotten the impression that concepts were there to express algebras, and my examples doesn't seem to reflect that idea, and I just don't think that idea is correct. It's not just for math, it's not just for things you have an underlying theory about. I showed mergeable, which is part of the standard library. That's for an algorithm, and I showed the input channel example where we're using concepts to constrain and specify actually the types that take part of a composition of things. So this was why I said it's not just for foundation libraries, which is a slightly stronger statement. I think it becomes very, very important in application programming. And I've seen that again and again. I've seen it in industrial code, and I've seen it very often in student code.
Right here. Okay.
Yeah.
Can you go back to slide 51 and just...
that one?
Yeah, can you help me understand what the error was that didn't get caught? And
Oh, an input iterator does not support plus. It only supports plus plus. So this is the kind of mistake that you can actually see in real life. Somebody had in their head the notion that that plus one and plus plus was the same thing, but it so happens that that's not the way it's defined, because plus one is to the type system basically the same as plus 20, and you don't want to be able to go 20 steps into a list, because that is an ON operation. And so we can't distinguish plus 1 from plus 10 or plus 10,000. And so the library is defined like that. And so this is the kind of mistake that we would sort of like to catch, but the side effects of catching that kind of thing is to close the interface around algorithms so that you can't debug, you can't have telemetry, you can't have gradual evolution, and you can't have stable interfaces. So we decided that this one, yeah, we would like to do it, but we don't quite know how yet. This takes more work. I think now, if you want to say something, please find a microphone.
Yeah, to go back to the point about algebras, I think in a more general sense, you do have some examples here like advance, where you're using concepts to constrain and to create an overload set. Right? Yeah. You have advance for forward iterators and for random access iterators. But then you have other examples like sort, which sort takes something sortable, merge takes something mergeable, in the standard swap takes something swappable. And it's a little bit circular, right? In that case where we become unclear, well, is it sortable because I can pass it to the standard sort, or is that a customization point where someone, with advance, you're using it as a customization point, right? Someone could add their own advance that was less constrained or more constrained, and it would pop into the overload set at the right point, which sounds horrible, but like that's the functionality you're enabling by using that as opposed to if context or something like that inside the implementation. With sort, are we using it as a customization point? Is that the reason for creating the overload set?
Yeah, I'm supposed to repeat questions. This one is a little bit hard to repeat, so I'll take it in chunks and repeat if I don't get to the real point. First of all, of course we can do it with algebras. We've done the monoid ring vector space stuff. On the other hand, we want the open overload that we get from C++, from the earliest days. I want to say I want to specify the algorithms in the standard library with concepts. And once you have done them with concepts, you actually will be able to add your own versions to it. Just you can add your own versions through overloading, or if you're doing object-oriented hierarchies, you can add your own versions by derivation. Now, some people call that ad hoc, and definitely meant to support that also.
But in that case, with sort, you're saying someone could add a more constrained sort that required sortable and also something else, and then that sort would get picked.
Sure.
But then you've got
I can use it both to get a more constrained version. So if you wanted a sortable that also could do foobar, whatever it is, you would simply take sortable and foobar. So you can get a narrower version, a more constrained version, as opposed to what I was doing was I was opening up. How do you sort when you don't have all the properties? You can do both. I'm going for flexibility here, not for any particular theory. And in some sense, any concept, any algorithm can be more or less constrained.
Hi. So I've seen, in the examples I've seen so far, mostly just checks for existence of operations on types, which is kind of something that we have been able to do before with enable if and stuff. Why does it stop there and not go further and also check between relations of operations? For example, for the concept equality comparable, it's not just enough to check that there's the operation equal and unequal, but also they should return the opposing value, right?
I think there are two questions here. The second one is, why can't we see semantic connections between the functions of a concept? We had a design for that for C++ OX called Actions, which I actually think is very good and could do exactly that. It expresses relationship between operations, and we just didn't think we could get that done now, and we didn't want to complicate the process through acceptance in the standards committee by throwing in more features.
Or is that where contracts could come in? I mean,
no, it's not. Contracts work on values. Concepts works on types, and it is still the type relations between the operations that we would be able to handle with concepts and with actions. There was a first part of your question that I don't think I answered.
I think I have my answer.
Okay, thank you.
I'm thinking about the operators which, like plus on signed integers, which are not defined for the whole range of the thing, or less than for floats, right? And you have the concepts which would cover these types, like sortable for floats, right? Would you include float to sortable or not?
I would definitely consider floating point numbers sortable, and I would just ignore not a number. There's been long debates about this, and it relates to the issue of whether a concept is a type of type. It is not. It is a requirement of what you get in, and as I pointed out repeatedly, it may not be the complete constraint of the implementation. It is still the implementation's job to know what is coming in case in case of a floating point number, it might get an n, and it is the algorithm's job to decide whether it wants to do anything about it.
Right, but then you wouldn't have the same semantics for example, plus. Plus it has not the same semantics between ints and floats, right? So if you have a number, that is not actually a number.
Do you want me to also do you want me to also check for overflow and underflow and everything?
Well, that is actually hard.
It is very hard. Checking for another number is very hard. Checking for another number only when you got a floating point type is very hard. If I was going to work things out for a small example, I might consider it, but I think it's a wrong approach for real-world scalable code.
Yeah, but that would result in incorrect code, right?
Yeah, I mean, it's a great help for thinking, but I think trying to constrain the concept use to things like that is wrong. I have another argument which I can't put my mind to just now. The not an n number was discussed again and again and again. I suggest you go to Andrew Sutton's talk about concepts. He's really good at that point. And isn't 2 hours into a presentation and a little bit woolly.
Hi. I'm a bit concerned about the kind of coarse graining of concepts. So you kind of addressed this preemptively. You talked about how plusable was not a good concept, and instead, okay, we have numeric, right? I think one of the issues with this is that, you know, in general, when you're designing classes, and especially for application developers, usually it's better to err on the side of a constrained interface. So, you know, if you don't need multiply, then you don't write it. You can add it later if you need it. If you think it's confusing or misleading, you don't have it. So we're in this situation now where if we start using this numeric constraint, in many, many algorithms, even though, let's say, multiplication's not used, like, I know accumulate probably isn't actually done this way, but imagine if accumulate was done using numeric, then suddenly, any type that I write that doesn't have multiply, we can't use with accumulate. So it's actually kind of encouraging people to like slot themselves into these concepts, which it can be a good thing in some cases, but I think sometimes it's actually pretty bad if you're basically saying to people, if you want to reuse this high quality generic code, you better add like all these other operations you don't really need and the algorithm doesn't need.
This is a very old debate. Should you have absolute minimal? Yeah, I'm repeating the question. Do you have absolute minimal requirements, or do you encourage people to build more complete types? And I don't think encouraging people to think about where their types fit semantically and put some extra work in is encouraging sloppiness. On the contrary, you need to look at experience, and my experience and other people's experience has been that encouraging plug and play, encouraging high-level concepts is useful and important. Furthermore, I'm not being rigid about that. Notice I said you evolve concepts, and furthermore, you can have various levels of concepts. It would be quite reasonable to have a concept for things that could be added and subtracted but not having multiply. So you have that flexibility. When you see a new feature, especially a major new feature, I find that programmers are amazingly good at imagining problems. And they are actually quite often dramatically lousy in imagining benefits. And my view is that any language feature, any concept, if you excuse the pun, has benefits and potential errors. And I consider software development fundamentally an engineering discipline as opposed to a branch of mathematics or type theory. And you have to evaluate the benefits and the disadvantages, and then you have to observe what happens in real life. And I have come to the conclusion after watching this kind of stuff and people using it for a decade plus that aiming for more general, more complete concepts actually improve code.
Thank you.
So with introduction of templates, we had to change syntax to allow things to be constructed with syntaxes intended for classes. So now we can use it for built-in types. So we made changes to the language to allow you to use it more uniformly. Now with concept, I see similar danger. The concept will be easier to use, obviously, but it could be realized in multiple ways. Do you see ways to change the language to help us realize the same concept in multiple implementations?
Not sure I understand the question.
Imagine that we talk about sortability. In future, you might be able to do it using the spaceship operator always. In the past, you would collect some other operators. You'd still get the same thing semantically, but it's really different implementation.
So the point is that you can implement things in different ways, and you need some freedom to do this. And that relates to the previous question. Do you define your concepts really tightly? Sortable is defined in terms of begin, end, and less than. That's what the standard says, and that's what the concept says. As a user, you then use the name of the concept. When the standard changes, say that sort uses the spaceship operator directly, your code will not change. Your requirement on your users may change, and you may have to fix that because the standard changed. But there's this indirection through the specification of the concept that gives you some freedom. And that your argument is an argument for the more general concepts as opposed to the minimal constraints.
I have a question about the relevance of constexpr in some of this. I know within a function, for example, if constexpr inside a template expansion has different properties in some ways than it does outside that, how would they constexpr interact with, say, function definitions and concepts with requires?
How would constexpr functions relate to the way it's used in concepts? Yeah. There are currently not in concepts a way of requiring constexpr functions, for instance. That is something we've discussed over the...
I was thinking more of trying to express test properties using constexpr instead of forcing people to use enable if. Inside a function, that's very simple, but I was wondering if there's a way to do that with
I would
as well.
like to see most uses of enable if disappear. They are more error prone, more complicated. You sometimes have to have both the enable if of a condition, the enable if on the opposite of the condition. If you have two predicates, you can end up with 4 versions of the code. This is horrid. That's eliminated by concepts. That helps. Constexpr functions fit with concepts because they both are ways of expressing a predicate if they return a bool. So it works together. There's a few rough edges. You cannot write a concept that says I require a constexpr function. By the way, code using concepts compile faster than code using workarounds. Eric Niebler reported 2 weeks ago that the ranges TS that exist in 2 versions, enable if and with concepts, compile 25% faster with concepts. Expressing things directly is better than representing things indirectly. And we're winning on all counts with concepts over the previous workarounds.
Thank you.
Regarding the idea of esfinay and default template arguments, template deduction, what is the opportunity that exists between concepts as it exists right now and the ability for those to participate in template arguments, in deduction, in esfinay style sort of errors that you may already experience?
The question is, how does template arguments fit into it? I think they simply fit into it. That is, you can express concepts that involves a template argument. Again, this is a level of detail I don't want to go into for the fundamental things, but I think you take the fundamental ideas, the fundamental techniques in the standard, and you pull the crank, and out comes the right solution.
Secondly, as well, with the ever-widening gap between C and C++ for this matter, there have been many features that have been introduced into the language over the years that have allowed me to do certain things that I could still accomplish and compile with the previous generation of our language. How do concepts and their forward/backwards compatibility, for that matter, restrict me from porting code or using development environments that exist in both C and C++?
Can you use concepts both with old compilers and C and C++ and C and C++? Well, concepts are not actually meant to be backwards compatible, obviously, and I think C is totally lost in this game because it doesn't have proper generics. You can't have concepts as a language feature supporting macros. And in practical terms, if you need to work on a variety of environments, some are old. You can use things like, if you restrict yourself to explicit requires clauses, you can you can have a requires macro that turns into nothing for old environments. And so what you can do is you can develop your stuff on a modern compiler, get the checking in place, do the testing on a modern compiler, then throw the switch so that the concept become nothing. And if you have not used overloading, it'll then run correctly on old compilers. A slightly more subtle version of that is to define your actual concepts as sort of capital concept macros that either turn into the concept for the modern compiler or to type name on the old one. Again, you lose overloading, but you can compile with GCC 4.2 if you're unhappy enough. It's pretty horrid, but there are ways of using older code, older compilers, but you have to do nasty things.
And will there be the ability to default or specialize on concepts within template programming?
Will there be a thing for defaulting, specializing? Specializing, yes. Defaulting, I don't quite understand what it means in particular, so probably. But
for another time, I suppose.
Yeah,
Thank you.
some other time.
Hello. I'm coming actually from a theoretical physics background, and I'm very excited about these developments that you've just talked about. I had a question. Some of what can be achieved very elegantly with concepts has previously been achieved by inheritance through abstract classes, and I wonder what is this take that you have on the position of abstract classes in the future with concepts being present?
So abstract classes versus concepts. One thing I failed to emphasize because I've become so used to it: concepts is a zero overhead feature. There is no runtime cost. And that's important, and I should have said so, and once you get used to things, you forget. So for abstract classes, if you want a binary compatible, upgradable interface, abstract classes are unbeatable. It's just a set of functions. On the other hand, it causes an indirect function call that can be expensive. Concepts are the opposite. There's no overhead. They're just compile time predicates. On the other hand, since concepts are independent of the layout of the objects they manipulate, they don't actually address the issue of binary compatibility at all. So I think they're sort of neutral. You have two orthogonal tools.
Okay, thank you.
So we do have 12 minutes of the next talk, so if you would like to ask Bjarne a question, maybe come to the stage and talk to him directly. We'll be setting up the next talk here.
Okay, thank you.
Thank you.